So, good afternoon, everyone. My name is Costa Christopoulos, and I'm a senior in EAPS with a double major in physics. And this afternoon, I'm presenting results for my thesis titled A Machine Learning Approach to Aerosol Classification for Single Particle Mass Spectrometry. And as Jay mentioned, this was done with Professor Dan Cziczo, whose lab is just down on the 13th floor. So before I get into the meat of the presentation, I want to briefly motivate the importance of distinguishing aerosols at the single particle level. So this was an image taken actually just last Tuesday from NASA's MODIS instrument aboard one of their satellites, Aqua. And you see large volumes of mineral dust being blown off of the desert. And this kind of hints at the importance of aerosols in the context of the atmosphere. They begin to interact with clouds and also radiation to affect the climate. So aerosols remain a very large uncertainty in the climate system. They are known to interact both with incoming shortwave radiation from the sun and also outgoing long-wave radiation from the Earth. Additionally, they serve as nuclei onto which water can condense and freeze to form clouds. It's also known that the large-scale behavior and characteristics of clouds can depend on microscopic properties, so microphysics. So things like the chemistry of aerosols, the size of aerosols, the morphology of aerosols. Additionally, very small changes in the chemistry can have large implications. So as an example, mineral dust, which traditionally acts as an ice nucleus, if it becomes coated in organics, it can begin to act as a cloud condensation nuclei. So this is a very different role in the atmosphere. Additionally, feldspar, which is a single aerosol within the mineral dust category, is thought to be the primary aerosol in mixed phase clouds. So although all these aerosols are treated the same, they may be doing different things. So this brings me to distinguishing aerosols with PALMS. PALMS stands for Particle Analysis by Laser Mass Spectrometry, and it's a single particle mass spectrometer. So for each aerosol it collects, it can produce a spectrum that looks something like this. So this is just mass to charge ratio on the x-axis, but these are singly charged, so it reduces the mass. And then ion current on the y-axis. And it's from this you can begin to get information about the chemistry of the particle. It's important to note that this is not the same thing as something like relative elemental weight percentages. This is a bit less quantitative because it depends on things like the ionization efficiency of aerosols. So the game we're playing is trying to distinguish these different aerosols in this space. And what makes this difficult is that aerosols can become internally mixed at the single particle level, so they can hold components of two different aerosols. So it's hard to classify it as either one of these classes. So this is what this looks like in this simple two-dimensional space. So along the x-axis is just peak 24, which is O2, and then on the y-axis, or carbon, C2 on the x-axis, and then oxygen on the y-axis. And you can see these different aerosol types separating out even with this, even with these two dimensions. So another complication of PALMS is that it produces only positive spectra or negative spectra for a single aerosol. So you have to run it in either one of these modes. Because of this, we're going to build two different models and then use them, combine them at the end. So to characterize the data set that's used to build these models, most of them were collected from the KIT Aerosol Interaction Dynamics in the Atmosphere facility. So it consists of 50,000 spectra corresponding to 21 different aerosol labels and 4 different aerosols categories. So I'm going to introduce some vocabulary here. Categories is just dividing it into these very broad groups, and then labels is looking specifically within these groups to see how well we can distinguish aerosols. So for example, in the fertile soil category, there's fertile soils just collected from different locations around the world, so they're very, very similar. And then in the other category, we see mixtures of the aerosol. So for example, K feldspar, which is here in the mineral metallic category, is coated with sulfuric acid and SOA. So this is where you begin to combine these categories. So once we've trained a model, we're then going to apply it to two data sets. One, both of these were part of a ice nucleation workshop. FIN1 was an international comparison study. It was a blind study, so researchers mixed 3 aerosol types, which were hard to distinguish together, and then 10 different instruments made measurements, and then the groups worked away at trying to figure out what was there. The second data set is collected directly from the atmosphere. So Steamboat, Colorado, about 2 years ago, the campaign took place there, and these correspond to aerosols just sampled directly from the free troposphere. So with the data set, we can now begin to build this classification model that I was talking about. And this is done using a binary decision tree. And this makes the classification by learning thresholds that it can compare each one of these variables to. So if you index each one of these variables, if you turn this mass spectrum into a column vector and just normalize by the total ion current, these are interpreted as variables. To build a model, it learns thresholds that can be used to separate, to make a decision about what class the spectra belongs to. So for example, in this case, the first decision will take the 15th variable. If it's larger than some value, it will go one way. If it's smaller than a value, it will go another way. And this corresponds to splitting this 1D space, different 1D spaces with this, with these thresholds. And at the end, it can, once you made a lot of decisions, you can make a prediction about what aerosol type is there. So in that 2D plot I showed earlier, this just corresponds to drawing a bunch of different lines. And you keep doing this until you can define boundaries that separate those groups of aerosols. And this is encoded in this tree.
Is the learning just for the thresholds, or is the choice of which ones you put into the notes, is that there as well?
No, yeah, so that's part of the algorithm. So the way each one of the splits is determined is it picks a splitting of the data that minimizes the entropy. If there's a high entropy, that means all the prediction labels are equally likely, and you don't want that. That's not a useful model. So it uses information entropy, and it's extremely randomized. So like to make each node, it picks a set of what it thinks are important variables equal to square root of the total number of variables, and then it randomly selects one of those. So the key here is randomness. And an additional random part of this is building an ensemble. So you don't only want to use one of these trees because it's easy to overfit. So we use Bootstrap Aggregation by randomly drawing from the full training set with replacement. So you create some new data set that doesn't have all the original samples. You then train a tree on that subset of the data, and then keep perturbing the data set and training a new tree. So each tree is seeing a different variation of the data. And then at the end, you just average the predictions of all the trees to make a final decision. And this is a well-known machine learning technique that improves generalization and prevents overfitting. Once the model is trained, we can evaluate the model performance using something called a confusion matrix. So this is just pairwise matching of model predictions as columns to actual aerosol types as rows. And these are normalized along columns. So if the model predicts fertile soil, 95% of the test set was correctly classified as fertile soil, but there was some confusion or misclassification with other categories. So you can kind of interpret this as a conditional probability distribution. Given some prediction from the model, what's the probability that it actually belongs to one of these labels? An important thing to note about how this was built is that we make a clear distinction between the training set and the test set. You don't want to use the same sample that was used to grow in a tree to validate the tree, because that's cheating. You're just giving the tree something it already saw. So we keep track of which trees didn't see these variables and only use those trees to make the prediction. So you can then divide these into those finer labels that I was talking about. And obviously when you have 21 labels, you expect more confusion because there's more ways to go wrong. So an important thing to note about this is that within the fertile soil category, we see an ability to pick them out with roughly 70%. So again, these are the same aerosols just collected from different parts of the world. And another thing that is expected is there's confusion between these potassium and sodium feldspar and then the coded versions of them. And this is expected as well because it's just, it has components of each one of those aerosols. So once, an additional benefit to using decision trees is you can begin to go back and understand which variables it used to make these decisions, and then kind of go back to the physics or chemistry to have useful information come out of it. So there's a variable ranking algorithm, which I will describe in a second, but we essentially, we select the most important variables for two reasons. The first is to understand what's going on. The second is to build a reduced model that has a subset of the important variables. We don't want to use all 201 variables because this is a very high dimensional space. It affects the convergence of the model and the generalizability. So we only select the most important variables using this feature ranking algorithm. And this is how it works. It's an iterative algorithm, so it takes a variable and it removes information about that variable from some test set, and then it evaluates how the model changes. So if there's a big change in the model performance, then that variable is probably important. And this is also averaged over all the trees. So it's meaningful because it's not a single tree that's making the decision, it's all of them. So once we take these important variables, we can build a subset, a model with a subset of them, and begin to make predictions about these blind data sets. So the first is the FIN3 data set, and unfortunately the researchers did not report the fractional percentages of each one of the aerosols, but just the aerosols that were there. This is something we're still working on getting. It turned out to be more difficult than we thought. But what was actually there was SOA and K-feldspar and soot. So soot was not considered by the algorithm or wasn't even measured by palms because it was too large. It was beyond the size cutoff, so there was just no spectra produced. So we can see how well it did for the remaining categories. And what we noticed is that it did pick up on SOA within 1 percentage point of, so this is the positive, results from the positive model and results from the negative model. So there's agreement there, and that was actually in the present set, in the data set. Additionally, it did pick up on K-feldspar, but interestingly, it also picked up on this coding. So because both K-feldspar and SOA were added, you expected there to be a coding. This was previously very, very hard to distinguish from either one of those aerosols, but this is picking them up at a significant level. So K-feldspar coded and SOA is shown here in green. These other categories are largely consistent with the confusion matrices. We saw there was some misclassification, so that gives you a sense of uncertainty. So you wouldn't want to consider these smaller amounts if you want to look at the confusion matrix and make sure it's consistent with the uncertainties. The FIN3 dataset presents another challenge because all of the particles in the population weren't contained in our dataset. In fact, only 10 to 20% of them are in our dataset. So we expect most of these particles to not be there. So unfortunately, with supervised classification, we'll always try to pick one of the categories that you showed it. So in order to take care of this, we want to look at a subspace that was well characterized by the model. If you plot the blind data that was, if you plot the atmospheric data that was unknown, it lies somewhere in here. So that there's like a mode here and the mode here. And you want to pick the part of the subspace that you characterize because that contains the aerosols that you're familiar with. So we use a probability density function to do this. And this is estimated using another machine learning technique called kernel density estimation. So this is just the probability density of the data set. And by picking a contour that encloses 80% of the data set, you divide it into a region that your model is good at classifying. So then we filter out the points that lie outside of this contour, and this leaves roughly 15% of the aerosol, so that's consistent with what we expect. And if you run the model on this remaining part of the aerosol population, these are the results. So fertile soils at 23%, the other category at 11%, and then mineral and metallic particles at 66%. If you compare this to some previous studies, so I looked at Professor Paul Demont and Professor Cziczo characterized ice nucleating particles back in 2003, and they found that 86% of aerosol in the atmosphere were sulfates and organics. All those weren't considered in this model. In the future, I would love to add them, but at the moment, that's how we explain the particles that were filtered out. And then he identified 58% of the ice nucleating particles as mineral and metallic. It's hard to compare the two studies because this introduces another category that was previously excluded because it's difficult. So that's roughly, this first order approximation at what's there is roughly consistent with previous studies. So in conclusion, I want to briefly summarize the importance of the benefits of automated classification for something like this. So for one, this reduces the need for qualitative comparisons between different spectra, which some previous methods were more subjective and qualitative, and this kind of automates the process for any set of aerosols. And this is a useful tool for augmenting existing classification tools. This is useful for augmenting existing classification. So clustering is sometimes used, but the difficulty with clustering is it will group aerosols which are different together. So for example, these coded categories. Furthermore, clustering doesn't explicitly rely on the labels. So we know we have labels corresponding to these aerosol types, so we should be able to use that information to make a better model. So in reality, the best strategy, I think, would be to combine clustering to get an idea of, to cluster similar aerosols, and then to understand what's in any one of these clusters, use this automated procedure to tease out what's there. And finally, this provides a general and flexible framework for identifying aerosols. So you can put any set of aerosols in this model. It's just one line of code, and then run it again and see what variables were important. Or you can just directly predict the quantities you're interested in. So for example, in models, you would want something like the nucleation temperature. So you can just put that as the output instead of any one of these types of aerosols. And that could lead to some very interesting results. So this concludes my presentation, and I want to briefly take a moment to thank everybody, beginning with Dan Cziczo, who provided me with many years of support. Maria, her last name is very hard to pronounce, but if you're familiar with the Cziczo group, you know who I'm talking about. And then Sarvesh Garmela, if anyone remembers him, he was here a couple of years ago, and he helped me out a lot with this. And then finally, my group of seniors, which we struggled together for a long time, and Jane for pushing us to actually do this. So I'm happy to take questions.